Here in example 1 from chapter 5, we've got a first order system with the input that is as shown, and when we want to find the forced response due to this input. First thing we need to do is put our equation in standard form so we can compare our results with the general results we've talked about in lecture. So we divide through by the coefficient in front of y. So this gives us a 1/2 y dot plus y is equal to 2u of t. So this is a tau y dot plus y is equal to ku of t. So for future use here, we're going to recognize here that the static gain is 2. The time constant tau is 1/2. So what we will do here is transform our differential equation. We get tau s plus 1 y of s, again for 0 initial conditions because we're looking for forced response. So that's equal to k u of s like this. So therefore y of s is equal to k divided by tau s plus 1. That's our transfer function times the transformed input there, u of s. So what is our u of s? Well, first we need to do our u of t. U of t, it can be made up of two parts. A ramp function, which is turned on at time equal to 0, and then we subtract away from that a ramp function, which is turned on at time equal to 3. So in the end, when we add those two up, we get the pulse here that we're looking for. So what I'm going to do is write this then as u of t, the first part, is going to be equal to 1/3 of the unit ramp, r of t, and I subtract away 1/3 of the unit ramp function shifted in time by 3. The Laplace transform of that is equal to 1/3 transform of the unit ramp is 1/s squared. And don't forget that when we shift the second one, we get the same as the first, except we get an e to the minus 3s as that. So therefore, our transform response y of s, I will have a looks like a k/3. I'll have a 1/s squared tau s plus 1 times the quantity 1 minus e to the minus 3s. So if we do our partial fraction expansion here, we have a fraction here of 1/s squared times tau s plus 1. So this has 3 poles. There's a repeated root there of s equal to 0. So we have a1 divided by s squared plus a2 divided by s plus a3 divided by tau s plus 1. And we do our work with partial fraction expansions. Don't forget the rules that are involved for having a repeated root. And we get that a1 is equal to 1. We get that a2 is equal to minus tau. And a3 is a tau squared. I can rewrite this last term here as tau divided by s plus 1 divided by tau. Basically divide the numerator and denominator by tau. So therefore our transformed response y of s is equal to our gain here of k divided by 3, 1 over s squared minus tau over s plus tau over s plus 1 divided by tau, all multiplied by 1 minus e to the minus 3s as that. So the inverse Laplace of this, we need to do this in two parts. Y of t, we're going to have the k over 3 out front. The 1 over s squared, that gives us a t, our ramp. We get 1 over s gives us the step function, so this is tau times h of t as that. And then we have tau times the inverse Laplace of the 1 over s plus 1 over tau, so that gives us a tau e minus t divided by tau. So that's our unshifted term. And then the next term is exactly like the first, except when we look here at our factor there, e minus 3s, every place we have a t, we need to shift that in time by 3. As that. Keeping in mind that our static gain here of k, up there we had that k was equal to 2 and tau was equal to 1/2. So the basic idea here is that we can take a fairly complicated input like this, and if we break it up into its basic parts here, the basic parts being that the ramp is made up, this pulse is made up of 2 ramps, one shifted in time and subtracted away from the first. So we took advantage of the shifting idea for the Laplace here to help us come up with our solution.